It's my pleasure to introduce today's IQUA speaker, Professor Luis Sánchez-Soto from the Complutense University of Madrid. Luis earned his PhD in physics from the same university in 1988 and has been a full professor of quantum optics there since 2002. Since 2009, he's also held a position at the Max Planck Institute of the Science of Light in Erlangen, where he leads the theoretical group in the division of optics and information. And so Luis's main interests lie in quantum optics and quantum information. And in recent years, he has been a leader in a flurry of work on quantum-inspired super resolution of optical point sources in space and time. And I think his talk will serve as a nice installment in a sequence of talks that we've hosted in this seminar series, including one from his experimental collaborator, Christine Silberhorn, about a year or so ago. So please help me welcome Luis. Take it away.
So thank you for the introduction, Michael. It's first of all, thank you very much for this invitation. It's a pity I cannot be there, but I mean this situation with the pandemics is really difficult for all of us. So as you see, yes, I'm as a real quantum guy. I live in a linear superposition between the University in Madrid and the Max Planck Institute, where I spent half a year every year. So the topic I want to talk is just how to achieve the ultimate resolution limits in general in quantum optics, okay? So what is resolution in general? So I would say that the resolution is just our ability to resolve two signals. That can be in the spatial domain, can be in the time domain, can be in the frequency domain, but they overlap. So the question is how much can they overlap and still being able to say, oh, they are two different signals. I mean, the standard example is in the spatial domain. We have two objects. We have an optical system with an aperture. We know that due to diffraction from the image of these two objects are two intensity distributions that are usually called the point spread function. It's just the shape of the intensity given by one of these single objects. And now the point is, of course, when these two objects come closer together, the intensities overlap more and more until one can really say they are resolved or not. This is the typical, as we know, in the case of diffraction for a circular aperture, the intensity distribution is this 80 rings. But if we take only the first ring, the intensity image from a single point is just a disk. When these two disks overlap, we know that the Rayleigh, the famous Rayleigh limit, is when the maximum of one point is just at the minimum of the other point. So this is just this here, these 2 points are, well, this is the opposite, are not resolved, and this is the area limit. So this Rayleigh limit was introduced around by this guy, John Strutt, although like 2 years before, this guy, Ernest Abbe, was able to give more or less the same explanation, although his paper is a long paper, no formulas, everything in German, and passed more or less unnoticed. So today to this limit is attached the name of Lord Rayleigh. So Lord Rayleigh, using this diffraction theory, was able to show that this minimal distance between these two objects is just given by 1.22, which is the first zero of the Bessel function G1, by the wavelength and divided by the diameter of the aperture. So this means if we want to have good resolution, we need big diameters and we need short wavelengths. if instead of having this angular separation, we talk about the linear separation we can resolve is just given by this standard expression. So if we apply this to the optical range, to the optical spectrum, more or less the resolution for typical microscopy is around more or less something around here. So we know that there are several techniques, okay, like all these around the 100 nanometers that allow one to go beyond the Rayleigh limit. All these techniques are called in a general form the super resolution techniques. Okay, we know all this. And now the question is, well, is this diffraction really a fundamental obstruction? Is the fundamental limit that prevent our resolution? And the same problem can be treated in the time domain. We have two pulses. When they overlap, of course, the intensity sum, and then the question is, how is the time separation between these two guys? And we still can say they are two different pulses. And the limit in this case is just the inverse of the bandwidth of these two pulses, which is just the Fourier transform of the duration. So what I want to present is just how to look at this problem from a quantum information inspired approach. So I look at the problem of this separation between two sources from the point of view of the quantum estimation. What is quantum estimation? Well, I mean, in principle, I have 2 point sources. I have an optical system, and then the two sources originate these two images that are separated by S. And I assume that the magnification of the system is unity. So the question is, how good can I estimate the separation between these two sources? The problem as such was initiated like a few years ago by Mankei Zhang, who published the pioneer result on this. And so let me give you in few minutes, in a few slides, what is parameter estimation in a nutshell, okay? So the idea is I have an initial state, classical or quantum, and this state I pass through a dynamical process, whatever that means. This means I put my state through a channel, and then I have a final state. And of course, the final state has imprinted the parameter of this dynamical process, the parameter I want to estimate. And then what I do is just a set of measurements, classical or quantum. And since everything is noisy, we have all this background noise. These measurements give me just a probability of obtaining the value of X. And of course, this is a probability that is a conditional probability on the true value of the parameter I want to estimate. And from this measurement, I ideally would like to give an estimator, which is just a function of the parameter of the data that allows one to infer the value of this parameter that is contained in the dynamical process. The only difference between quantum measurement or classical measurement is that the quantum measurement is usually treated like, according to the Born rule, is the trace of it's called a P of EM that describes the measurement, and rho is the density operator. But otherwise, this is a classical probability distribution. The only thing is when I try to extract the estimator, I have to be careful that one has to preserve the positivity of the density matrix. So from this point of view, there is nothing intrinsically quantum in this quantum state estimation. It's just classical parameter estimation plus the constraints imposed by positivity. But otherwise, once I have this, the question is, how good can I estimate the parameter of this dynamical process? So when the estimator is unbiased, that means that we don't have any bias in the average. We have this famous Kramer-Rao bound that tells us how good is the noise, the precision of every estimator we can use. And we know that the best we can do, this variance is always greater, or the best we can do is equal to the inverse of the Fisher information. N is the number of times we repeat the experiment. And this Fisher information at the classical level the classical Fisher information is given by this formula. And forget about the formula. The only thing we need to recall is that the Fisher information is just the curvature. So it's just the information that we can extract from the experimental data. And this is given by the curvature of this probability, which is called the likelihood. So one can think, look, but this depends on the measurement I perform of the state. And that's true. At the classical level, every measurement gives a different probability distribution. And therefore, I can only assess the goodness for a particular measurement. One can say, look, can I optimize overall possible strategies of detection? Can I give the best detection scheme that allows me to attain this inequality? And the answer is yes, I can make this optimization of overall these possible strategies, overall this possible POVM. And the final result is just the quantum Fisher information, which has a good thing. And the point is that it depends only on the quantum state, but not on the particular measurement we perform on the system. So now let me go back to the problem of estimating 2-point sources. So let me call psi plus one of the sources, the source which is in the positive x-axis. Let me call psi minus the source that is on the left. And then the density operator. So what I have is essentially 2 modes, 2 levels. It's like a 2-level system. And the question is that when we apply the Rayleigh criterion, we assume that everything is incoherent. So the intensities of the sources are sound. So this means that the density matrix of these guys are just the incoherent sum of these 2 modes. And of course, psi plus and psi minus are just displaced version of the PSF. So I take the PSF and displace to the left, to the right. And then I have, this is my density matrix. And of course, the density matrix depends on the separation of the 2 sources. I call S the separation between the 2 sources. And of course, if I represent this guy in the position representation, so I project over intensity, over position, what I have is just the incoherent sum of the intensity produced by this source and the intensity produced by the other source. The problem of this is that these 2 modes overlap. They are not independent modes. And this overlap is just the origin of the Rayleigh criterion. Let me now consider the case of intensity detection. What is intensity detection? It's just making a projection on the position. I know the intensity at position X. So I make this projection here, and I apply the definition of the Fisher information. This is the classical Fisher information. Remember, it's just the curvature And if the two sources are close enough, then I can make a Taylor expansion here. And what I get is just a trivial calculation. The question is, I get here this, which is just a number. And then the Fisher information depends quadratically on the separation. So this means that when the two sources come closer and closer together, the Fisher information goes to zero. This means we don't know anything about the system. We cannot extract any sensible information. And as a consequence, if you remember, the Cramer bound says that the variance of any estimator depends on the inverse of the Fisher information. If the Fisher information goes to zero, the variance of any estimator diverges. And this is just a mathematical statement about the fact that we cannot say anything about the separation between these two sources. So the variance blow up, and this is what right now in the last years has been called the Rayleigh's curse. Is that a fundamental issue? It's just a fundamental limit that we cannot really escape? Well, I think the answer is no. And the answer is no, because the intensity detection is just neglecting all the phase information, so cannot be complete. So in other words, can we dispel the Rayleigh curse? And the idea is we need to make a measurement that incorporates all the information available in the phase that is discarded by the intensity detection. So let me just propose just that the measurement, instead of projecting on X, which is just projecting intensity, I project in a complete set of modes. What are these modes? Any complete set of modes. I project on these modes my density matrix, and the only thing I impose is that these modes should have a definite parity. So in a way that measurement does not fill the two-component structure of the system. Well, if I do that and I calculate the Fisher information, it turns out that the Fisher information is constant. And the quantum Fisher information is constant. This means that when the two sources goes to zero, the information is the same as when they are separate. The information is not changed. And therefore, I can estimate the separation even at the limit when the two sources are close to zero. So in a way, yes.
And Luis, are you taking questions during your talk?
Absolutely, absolutely,
Yeah.
anytime.
Can you just say a little bit more about these modes, what they are? Are they spatial modes? Are they pulses that have a certain time interval? And then also, what about parity? Yeah.
Give me I will, so right now, the only thing I need thus far is that they constitute a basis in the Hilbert space, as a mathematician would say, okay? But then what are they? I will introduce. So the easiest way to give the
sorry, Luis, can I ask another question for the page before?
Of course, anytime. Yeah.
So if you calculate this is for a fixed n, or you sum over all n? I just don't understand in this equation.
No, sure. I mean, yeah. No, you project over the whole modes. So n is this. I mean, I'm assuming that the modes are discrete, because in the lab,
well, sure,
use discrete
you're in the
modes.
finite dimensional Hilbert space, so what, right?
Exactly, but I need to project over the complete set of modes. So I need to make.
And then you're summing up over all n here, sort of implicitly.
No, I
right?
don't sum. Yeah, of course. For getting the whole Fisher information, I need to sum over all the modes. However,
but this is for an individual one.
Yeah. Okay. But let me go a bit more, and I will try to convince you that the advantage of the method is that in practice, only one single mode gives you 99% of the information. We don't need to go to infinite number of modes. In principle, to recover all the information, we should get all the modes. In practice, only one. So this is something I'm not entering, but what are these optimal modes that collect the most in the most effective way the information? So I don't want to enter into the technical details, but the recipe is very simple. You take your PSF, so you take the wave function of one of your single source, and you take all the derivatives, infinite derivatives. And then for every derivative, you get one of the modes. So in principle, you get infinite number of modes because you need infinite number of derivatives. Let me give an example. So if you have diffraction and in the spatial domain, okay, so you have a single source, you have a circular aperture, you know that your point spread function is just 80 disk. But you know, the question, the 80 disk, as we know from Optics 101, is just J1 functions. And working with the Bessel functions is always a bit annoying. However, we know that if we restrict our attention to the first maxima, to the first disk, this can be easily approximated by a Gaussian. So I take my point source, describe it as a Gaussian. Of course, sigma is just the width of the Gaussian. And this is just, I mean, you can take that in the spatial domain for the 80 disk, in the temporal domain for a Gaussian pulse, in the frequency domain for a Gaussian spectral line. And now you take the derivative of the Gaussian. So you take the derivative of the Gaussians and you make you orthonormalize the solutions, and these guys are nothing more than the Hermite-Gauss modes. Is that answering the previous questions?
Yeah, thanks for doing that.
Yeah.
So in principle, now that you have the recipe, okay? If you give me your PSF, or I mean, PSF is typical a name in the spatial domain, but you give me the shape of your pulse or the shape of your spectral line, take the derivatives, and you know how to where to project. So Gaussian is simple because, of course, it's the Fourier transform of itself and works pretty well. But I mean, imagine you have a slit. So now instead of having a circular aperture, you have a slit. What is the slit? Is just the sinc function. Okay, so you take the derivative of the sinc functions and you orthonormalize, and then you will discover that then the modes are Laguerre projections. But so in principle, you always get an orthonormal set of modes that are the guys you have to project. And interestingly, if you project over all those modes, you will get that the Fisher information is just 1/4 sigma squared, and sigma is just the width of your Gaussian. And so this means that there is nothing that diverges when the sources come close together. And the point is that the intensity detection, that is usually the method of choice in the lab, is not good enough to catch what's going on. So immediately after this proposal, there were 3 groups that they were working, or we were working. So this was the first paper appearing in Optica in 2016. Alex Vosky was the second one, and Ephraim Steinberg It was a bit later, although to be honest, Ephraim was the first one starting the experiments. So let me show you our experiment, but I mean, I'm telling you that I'm a theorist, so I did the calculations, but the guys in Czech Republic did the experiment. So what we did is we took a DMD, which is a digital micromirror device. So in a way, this is just made of small mirrors, and we make two of the mirrors to work in the reflecting modes. So this means that when we illuminate with a helium neon laser, we have two sources, almost point sources, in which we know a priori what is the separation. Then we took a optical system, in our case was a single lens, and here, instead of making intensity detection, so putting a CCD camera or putting a screen, what we put was a spatial light modulator in such a way that projected onto the modes. And the answer, and now the question is, how many modes? In principle, my answer will be infinite modes. However, the real situation is that projecting on the first two modes gives you 99% of the feature information. So only two modes is enough. You know, in the old times, this idea of projecting to modes was started by guys in Australia, Hans Bachor, and Gauss in Paris, Claude Fabre and Nicolas Trepp, and they call that the detector mode. So if your signal is in a Gaussian, your detection should be in the derivative of the Gaussian.
Luis, can I interrupt?
Yes.
Can I interrupt for a second? So in this experiment, are you taking into account the diffraction efficiency, not of the SLM, but of just the fact that most of the light, you know, by the laws of optical physics, like, is going to end up in the unmodulated part? So how do you deal with that?
We have to correct, because in the end, this is an estimation problem. Okay, it's a computational problem. We have to take we had to take care of the, I mean, first of all, the diffraction. First of all, the experimental setup was not, let's say, very good. And the diffraction efficiency was less than 1%, was very poor, okay? But corrected by all that. So I can show you here, this is the mean square error, which is probably this the variance, okay? And what we have here, this red line here, is just this, the Rayleigh limit. As you see, as the separation goes to 0 in units of the sigma of the Gaussian, the variance diverges to infinity. This means we cannot estimate. And however, when we project it onto these modes, you can see here that we were able to. Is there any question?
It looks like Paul has a question.
Well, but keep finishing your sentence, and then I'll ask my question.
Oh, sure. Then you see that projecting in these two modes, these crosses are experimental detection, and in this particular experiment, we were able to beat the Rayleigh limit by 17. But right now in the lab in Paderborn, we are beating the Rayleigh limit by a factor 10 to the 3. Yeah, and so go ahead with your question.
So in this experiment, I'm trying to understand what the two sources are, and it looks like you have this Heaney going off the deformable mirror, the digital mirror device.
Yes.
And earlier on, you made an assumption, and maybe the assumption doesn't hold for this analysis, but you made the assumption that the two sources were independent of each other, that they were incoherent.
Yeah, sure. Yeah.
But here, of course, the Heaney laser is not incoherent; it's a coherent source.
Yeah. No. Yeah, you are completely right. Well, first of all, pardon me, I'm the theorist, okay? So, but yeah, so what we did is that these micro mirrors, these two independent mirrors are vibrating each other to make them incoherent. That was the, yeah. So I will go to the coherence immediately, okay? So I think I have still like 10 minutes, a bit more, okay? So we did the same just recently in the time domain. So we used to project on these modes some setup that is in the University of Paderborn, and Christine Silverhorn was presenting. She called that the quantum pulse gate. And the quantum pulse gate essentially just projects the signal in the time domain into this mode. So you have here the two pulses, and this is the projection. This is in the time domain. This is in the frequency domain, which is just the Fourier transform. In any case, here, as you see, there are the two pulses that are separated. In principle, you see this is experimental, the two sources. In this case, in this experiment, we were able to beat the Rayleigh limit in frequency by a factor 10 to the 3. So in a way, we were able to resolve two spectral lines that are 10 to the 3 times below the Taylor or the Rayleigh limit. So we are using this technique to make, for the first time, a real quantum spectrometer. Okay, let me go. I mean, one of the hypotheses that the two sources are incoherent, but also that they are equal. However, in many instances, the two sources have different intensities, of the two pulses have different intensities. So now imagine I want to estimate not only the time separation or the spatial separation, but also this intensity imbalance. And of course, I need also to figure out what is the centroid of these two guys. So this means that now we are not estimating a single parameter, but we have to estimate 3 simultaneous parameters. And this is a problem which is called the multiparameter quantum metrology. And now, whereas in the single parameter case, we always can find a strategy that just attains the Kramer bound. In this particular case, it's not always guaranteed because these parameters cannot commute in principle. So instead of having a normal quantum Kramer bound, we have a Fisher information matrix that can be obtained according to some rules. It's called the logarithmic derivative. And the quantum Kramer bound is now a matrix inequality. So the question is, what's going on when I want to estimate these things together? So this is theory right now. I'm plotting here when two sources are really equal and incoherent. As you see, the separation can be estimated with constant. And now here is where the two sources are imbalanced by a factor 0.012, 0.25, 0.36, 0.4 more or less. So as you see here, instead of plotting the variance that diverges, I plot the inverse of the variance, which is called sometimes the precision. The precision goes to 0. So this means that when the two sources are different, we have Rayleigh curves. We cannot determine, we cannot assess anything when the separation goes to 0. However, I'm plotting here the corresponding limits when instead of making these mode projections, I make intensity detection. And as you see, from here to here, there are immense, especially if I try to make imbalance to estimate simultaneously the imbalance between the two sources. Look at here, versus the corresponding for intensity detection. And this means that this method is not only that giving you the source separation, but the difference in intensity. In fact, you know, I was telling before, I mean, the European Space Agency approaches us and they are interested not in the technique of mode projection for the estimating the separation, but they are interested in making this for intensity imbalance, especially because they want to estimate the exoplanet detection. So we did also the same. This was theory, and we did this experiment in the time domain. So we have two incoherent input pulses, and we need to project simultaneously to detect the three quantities of interest. And of course, if we want to project, we need to have and make the estimation of three quantities. We need to project simultaneously at least in 4 modes. 3 of them gives the 3 quantities, and 1 of them is to ensure the normalization. So these optimal modes can be obtained by a technical procedure. I'm not entering into details, but I mean, if you want to discuss later. So what we did is use these are the shapes of these 4 modes. So we input with this, we enter the system with these incoherent input pulses, we project into the modes, we detect, and these are the experimental results. This is the simultaneous estimation of the time separation, the intensity imbalance, and the centroid for 2 pulses. All these shaded areas correspond to the classical forbidden region, as you see with more or less experimental errors. The quantum Fisher information is constant, and this method has allowed to estimate simultaneously at the quantum level, attaining the quantum Kramerov bound, the ultimate limits, simultaneously the time separation, the intensity imbalance, and the time centroid of the pulses. So to conclude, let me just mention a question that has been under a very, very heated debate in the last 6 months. What's going on when the 2 pulses are partially coherent? And the answer is a bit, I mean, there was papers by Mankey-Sang, papers by Baja-Chalet with different conclusions. And the idea is, well, we need to make the experiment and to check. So what we did is to use 2 different pulses and change the temporal coherence between these 2 guys. So in principle, we have 2 pulses, we make 2 delayed copies of the pulses, we know this time delay, and then we are able with this quantum pulse gate to generate the in-phase and the anti-phase superposition of these guys. So this means that the symmetric mode is the in-phase sum, the anti-symmetric mode is the anti-phase sum. And now we make the experiment, we make the detection. So what's going on with the incoherent source, when the incoherent superposition? So you have the Fisher information for the symmetric and the antisymmetric modes. And when you sum these 2 modes, they saturate the quantum Fisher information. And so they saturate the quantum Kramerov bound. Sorry, when you make now the coherent superposition, so for this symmetric mode, the quantum feature information, the quantum feature information goes to 0, while for the antisymmetric mode, the quantum feature information goes to the quantum limit. So this means that the quantum feature, the total quantum feature information goes, also saturates the quantum Kramer bound, but in this channel, which is the anticoherent, the number of photons goes to 0. So if you prefer, I don't want to enter into calculations. I mean, when you go to intensity, when you go to a coherent superposition, what you get is interference fringes. And of course, we know you have maxima and minima. The minima are 0. So all the information is concentrated near the minima, where the intensity is starving. We don't have photons there. So this means, sorry, that when you have partial coherence, what we do is just redistribute the information into these two interference channels, but still the Hermite-Gauss temporal modes are optimal and for any degree of coherence. So we did the experiment with this. We did the experiment. This is the quantum. This is the Rayleigh limit, and these are the quantum Kramer bound. The experiments. These are different symbols for different degrees of coherence. As you see, for any degree of coherence, the quantum feature information is constant. So there is no Rayleigh curse, but at the price that one has to be careful with the resources, with the number of photons we are getting in our detection. So just to mention the experimental groups that have been involved. So this is University of Paderborn. This is the University of Pulaski in Olomouc, University of Ottawa, the Moscow State University. This is Seoul National University, and the University of Roma Tre with Marco Barbieri. And with that, I thank you for your attention. I'm taking any question you want to ask. Thank you.
Thank you, Luis. It's really cool. So we've had a good discussion while this talk has been going, but could you maybe shed a little more light, add a little more detail to how one might adjust their experiment, given the knowledge, if they know that we've gone now from incoherent pulse pairs to coherent pulse pairs? Is it I changed my gating pulses basically with that knowledge, or?
Okay, no. So in the experiment, they tried to change the coherence in the setup. So they weren't able to do that properly. So what we did is post-processing. So we generate the in-phase and the anti-phase pulses. So the in, and then with these experimental results, we made superposition of these two guys, because these two modes constitute a basis of the temporal modes. Yeah, it's not.
So you use the same gating pulses, but it's just where.
Sure.
Most of the photons go from here to this. Is that right?
The only question again. So I mean, the mode projection is still optimal for any coherence.
Right.
So the only question is that, of course, all the information in this particular case is just in the zones of your interference in which you don't have any photons. So you need to be extremely careful with your resources. So in a way, if you are making classical interferometry, you know this method of the dark fringe. So the most of the information is in the dark fringe, where there is no light. Okay, and the same is here. So the partial coherence redistributes, okay, the information through all these channels, okay, the in-phase and anti-phase and is sending more or less photons to one or to the other. If you prefer, when you normalize your two states with coherence, okay, the normalization depends on the separation, and this makes things a bit more complicated from the point of view of theoretical point of view. But the final answer is the ultimate limits for incoherent or coherent superposition is the same. The method, the optimal measurement, achieving the quantum grammar bound is the same. However, the resources, the intensity you get, the number of photons you get in the channel you want to estimate is changing radically in a very abrupt way.
Right. So it would inform you to, like, based on the coherence, you should either spend most of your time measuring the projection onto the symmetric.
Exactly.
Versus, yeah. Okay.
Exactly.
And so presumably you could also
Law.
turn this around and make it make a good estimator of the degree of coherence too, right? I mean, is there any advantage to that?
Right. Right. This is a proposal by Nick Vamivakas in Rochester.
Yeah.
To use this method to estimate in a more precise way the temporal degree of coherence. You know, I was mixing a bit spatial and temporal domains, because sometimes for some particular things the spatial domain is more clear. However, you know, in the spatial domain you have two different, because you have, you know, the longitudinal and transverse resolution, while, you know, I mean, axial localization or transverse localization. However, in the time domain, you don't have that. So it's a single, you know, coherence, okay? And from that point of view, this is, I think, well, Nick is now is ill with COVID, but he is thinking in making the experiment. Yes, that's a.
Any other questions?
I just had a question, sort of a follow-up on some of the things I was wondering about earlier. In your introduction, when you were discussing the Rayleigh criteria, you said that the way you're going to get around this is to use the phase information of the light. And you did that for, most of your discussion was involving incoherent pulses. And then you, at the end, were discussing coherent or partially coherent pulses. And so my question is this, you know, when I think about coherence, I think that that's where I'm going to be seeing the phase information being made use of. But it seems like you were able to get this out, your result out here involving your criteria here without having coherence. And that means to me, no phase information. So maybe I'm misunderstanding something.
No, probably, yeah, sure. I mean, probably it's just I didn't tell things in the proper way. So when you make intensity detection in any signal, okay, irrespective you have one or two superposition. What I mean by intensity detection is you just detect. So you just detect. Sorry.
Square law detection.
The square, the complex. Okay, nothing more, and you are losing information. Period. So when you make this intensity detection, you are losing all the information of the phase of the total field. However, when we project into these modes, is a way to recover the whole signal. I mean, if imagine you have in quantum mechanics your wave function and you project onto X, and then you take the absolute square, okay? So you get the probability distribution. But however, you can project, for example, in any discrete basis and measure any of these guys. In a way, you projecting into all these modes instead of a single X, you can extract, even if any of this measurement is incoherent, but you can reconstruct the phase of the state. If you prefer in another way, when you project into position, so from a technical point of view, intensity detection means you project on X, okay? So you know the intensity in X and you take F square. However, this projection on X has no definite parity. So you cannot detect the structure of the field. However, the mode projections are able to detect. So you change to modes in which you don't have overlap. They are independent modes. And this is why this overlap is preventing the proper estimation. I don't know if this.
Maybe you go back to your experimental setup.
Sorry?
Maybe you could go back to the slide that shows your experimental setup and the way in which this projection is done.
So yes, here, once you have the two incoherent sources, and this SLM is at the situation of this, this is of the image plane, okay? So instead of putting the CCD camera, we put a spatial light modulator that is programmed to project onto these, the first and the 0 and first mode of the Hermite-Gauss modes. And from that, we are able to reconstruct. In principle, as I told before, we should project onto infinite number of Hermite-Gauss modes. However, the first two are enough. And of course, you need to make computation because this is a computational estimation. So from this experimental data, we record these intensities and we invert the system, and we are able to estimate in a clean way, I hope, the separation between these two sources. So the method is called SPADE. I mean, was called SPADE by Mankey-Sack. But you know, this mode projection, I mean, there are, I was mentioning before, there is even a couple of companies in Europe. One is in France, it's called Skylabs, and the other one is Skylabs. The other one is in Oxford, is M², in which essentially what you get a signal from an optical fiber, and the Skylabs can guarantee you that you can take your signal and project simultaneously in any set of modes. In principle, up to 56 different modes simultaneously. Okay. And so this is well, what they have is spatial light modulators and projections in mirrors. So they can take the light with a mode structure from one fiber and change the mode structure just to couple to another fiber. This is the same idea. This is, and M² is interested in using this detection just to apply this mode projection instead of the intensity detection to spectral and to quantum spectrometers, to use this in the frequency domain, so you can really go beyond the Rayleigh limit for spectral lines.
And so in that picture, if you had only one beam instead of two beams coming from the digital mirror there, then one of these modes would disappear.
Exactly. Only the fundamental mode, yes.
Yeah.
Because the signal is just already in one eigenmode. Exactly. Yeah. So it's just to make the appropriate mode. In fact, you know, usually when we look at at the beginning for what is the optimal mode, so what we did in principle is decomposing this experiment in any kind of modes. So we used Hermite-Gauss, Laguerre, any kind of modes, and we discovered that with Hermite-Gauss in this particular case, two modes were I'm not sure about the figures, but I think 98% of the total feature information. However, we projected in Laguerre, and the result is to get the same. Instead of having 2 modes, we needed 5 different modes. And instead of Laguerre, we used spheroidal prolate modes. And we needed like 12 modes to get the same information. So in principle, the idea is, no, project into any set of modes. What I'm saying is, I don't want to enter into technical details about optimality. What I'm saying is, if you do the recipe and you take the PSF and take the derivatives, I mean, you will need only a few mode projections. Of course, there is something that I don't, if you continue here on the right-hand side, separations, I mean, larger and larger separations, you need more and more modes, but then intensity is optimal. Of course, I mean, when you have two separate sources, you don't need to do anything. So the advantage of this is that the method requires less and less modes when the sources are closer and closer together, which is precisely the region where classical optics is failing. This is the good thing about this.
Maybe one more question, let's say, from Paul.
Well, I could hold it in the sense that I'm actually the person who's speaking next. But I guess I will just ask it because it might be of use to other people. So I'm trying to understand this difference of coherent, of the fact that we're getting the phase information. And it seems to me it's the odd parity states that somehow are more interesting, right? Because the fundamental, the picture that you get doesn't really care. There's no relative phase between one part and another. It's when I go to the odd order parity, that then if I look at the diagram you have here, the 2 lobes, if I just take the intensity, I don't know that there's a pi phase shift between those. But when I can get the phase information, then I get that extra fact that they are 180 degrees out of phase, and somehow that's the relevant piece. Is that a way to think of it?
Yeah, no, it's completely true. I mean, this is the way of the parity is able. I mean, adapting the parity to the system is just the way to get the phase information. I mean, look, in the first experiments these guys were using, I mean, Hans Bachor, they call the quantum laser pointer. Yeah. And the idea is that, I don't know if you remember the paper, but okay. So the idea is, if you have a mode, like it's a Gaussian mode, and you want to detect, the best you can do is to use what they call the mode detector. What is the mode detector? It's just choosing the proper parity. What is the proper parity? The first derivative. And they call that the mode detector. The only difference here is that to get the whole picture, in principle, you would need infinite modes. However, we are lucky that when you choose the proper modes, the first is enough.
Yeah, great.
I don't know if so it's not like probably this is what is, you're right. It's not that in any of the single mode projection we are gaining any phase. It's just the parity of the modes that allows you to recover the whole information of the field.
Yep.
Okay, so thank you, Luis, for really interesting talk and
thank you for
great discussion.